me just see, why can't I?
This meeting is being recorded.
Okay, can I start?
Yeah.
Can you hear me? Can you hear me?
Yes, go ahead, please.
Okay, thank you so much. Thank you for inviting us. It's a privilege to be part of this. So me and Alicia are co-workers at the University of Stellenbosch in Cape Town, South Africa. And we manage the scanner electron microscope lab and helping and assisting everybody in Stellenbosch campus and other universities across Africa. And also lots of industry clients use our facilities and and sending samples to us on a daily basis. Okay, so Alicia, can we go to the next screen?
Yes, here we go. Sorry.
So our overview we can discuss is introduction and the principles regarding SEM, scan electron microscope. And we're going to have a quick view over transmission electron microscope, colorative electron microscope, and also how to prepare the samples for these different techniques and applications. And then Alicia's going to talk more about the polymers and nanomaterials. So what is scanning electron microscope? So scanning electron microscope produces images of a sample by scanning the focus beam in a raster mode on the surface of the sample. So scanning electron microscope is basically a surface analysis. So the electrons interact with the atoms in the sample, which then produce various signals, which then can be detected and then give you the information about the surface or the morphology or the composition of the sample. The electron beam is generally scanned in a raster form, and the beam is positioned and combined with the detected signals and produce an image. So the SEM can then achieve a resolution under 1 nanometer scale. So everything in the SEM happens in a vacuum. So there is certain principles regarding a SEM to understand. If you understand the principles, you will be able to add and use these principles to know what type of sample will work and what type of images you will require, and also help you understand what you can get from the SEM. So the SEM is composed of several primary operational systems, vacuum. Everything happens under vacuum. So that will also then you get an idea of if something happened under vacuum, that the sample must be able to withstand the vacuum. So therefore, we prepare samples with different sample preparations, so the sample can keep the integrity while you view and analyze the samples under a certain pressure. And certain SEMs have certain pressures, so you get different types of scanning electron microscopes. This requires different vacuum pressures. And these different SEMs is depending on the high-end scanning electron microscope, like we have in our lab, is the Merlin field emission SEM, which then require a very high vacuum system. And this vacuum system never really breaks while you're loading a sample into the chamber. So we have a sample loading system where you load the sample, and the sample then the loading system then generates a vacuum. And once the vacuum is reached similar to that inside the chamber, we then transfer the sample into the chamber. So the vacuum inside the chamber and the microscope will never be break. So that's why we keep this vacuum at a very high vacuum. And this is basically that sets this apart from other microscopes. The normal entry-level SEM, which use a tungsten filament, they have a much lower SEM, where you load samples from the chamber, so you break a complete vacuum inside the microscope, and that vacuum is then much lower than that what you get from a field emission SEM. So that will also then tells you also about the resolution of that types of SEM. So scanning electron microscope with very high vacuum will give you a much higher resolution. A scanning electron microscope with a much lower vacuum of 10⁻⁵ that will give you a microscale resolution. So the next is your electron gun. So electrons, get generated, and the primary electron beam at the top of the column. So there are two types of beam emissions that get excited off the filament. The thermal emission, that's where the electrons are extracted from a heated filament by applying high electric potential between the filament and an anode. So you get then different types of beam sources. So you get the tungsten filament, which have a vacuum of -4 to 10 to -6 vacuum, but that's where you get macroscale images. Then you get your lab 6 filament, which give you a higher resolution. So you get a higher contrast, and it's a higher lifetime, a longer lifetime, and the resolution is much better than that of a tungsten filament. The tungsten filament is a shorter lifetime, but it is much cheaper to replace than that of a lab 6, which is a little bit more expensive. Then you get your field emission. So your field emission is where you get a cold field emission, a sharp single crystal tip mounted on the hairpin filament. So this basically is a crystal of a tungsten crystal, and that requires a much higher vacuum and a much higher electric field, which then is applied between the aperture and the anode to introduce electric charge. Through that tunnels through the barrier at the ambient temperature. The advantages is that it cools emission. A narrow beam fits a size of -5 nanometer scale and longer filament lifetime. So the high vacuum is definitely needed in this case. So you get a much higher lifetime, a longer lifetime, but it's a very much more expensive source of electrons. And this is something that cannot be replaced if it's reached its lifetime period. It cannot be replaced by an analyst. You must get an engineer in to replace this, and it's very expensive. Thank you.
Sorry, can you just see what's going on?
Okay, so you get also, if you understand how a scanner microscope look like, the whole top gun area, and in the gun area where your beam, I just discussed before, is your source of your beam of electrons, where your beam gets generated, and that beam of electrons now accelerate now down in the column, and in your column you get your different lenses and coils, and these lenses and coils help you with the focusing of your beam. Okay, so the system consists of electromagnetic lenses and coils that is located in the column. And then the condenser lens is then performed, the spot size control by converging the electrons beam to a spot below before the cone flares again and is converged back again by the objective lens and down to the sample. So the beam passes through the rastering coils, through 2 sets of magnetic scanning coils and beam scanning in both X and Y directions. The magnification is controlled by modulation scan area, and it creates a large magnification. So your final lens of where you focus is actually your objective lens. So the beam, So your final lens of focusing onto your samples, your objective lens, and this is necessary to have an image in a proper focus mode. So your signals that you then detect in your sample is a secondary electron signal where you use a secondary electron detector. So this detector is mainly used for morphological surface topography. So you can see clearly what's happening on the surface of your sample. You can see the morphology of the grains, the angularity, and you can also view the different surface features on your samples. There's airy pores, or you can view that with your scanning electron microscope. Then you get so your scan electron detector also requires a much lower beam current. So different types of samples requires different beam currents depending on the type of sample, and it also depends on what detector you will use and what features you want to showcase on your sample. Then you get your backscatter electron. So your backscatter electron is more for a higher voltage current, and this is a image that you can generate based on the atomic levels, that you can view the different atomic features or different atomic phases on your sample. So this is for much higher atomic level images or phases you want to view based on the contrast levels of those different atomic levels. So the higher atomic phase, the brighter the phase. If you have a low atomic phase in your sample, it will project as a darker phase on your sample. For instance, if you have a combined mixture of samples with different types of chemical compositions, and then you can view these different features based on the grayscale of that specific phase. So the backscatter intensity is then proportional to the mean atomic number of the atoms, and therefore provide information on variations of the sample composition. So basically, what does it mean? That means whatever you put in, electrons in, you get different signals that comes out. So the different signals that comes from your sample is dependent on the signal you introduce into your sample. So the higher atomic phases, higher kilovolts, electron beam with a higher kilovolts will generate backscatter electrons. Electron signal with lower kilovolts will give you more secondary and primary electrons. And you can get also cathodoluminescent signals also from your samples, where you get it due to photons. So the detectors all project what amount of electrons you introduce towards your sample. Okay, so the types of electrons. So I touched on this a little bit in the previous slide. So what is it on? How deep? Most of the time, students will ask me, how deep does a beam penetrate into your sample? So the beam penetration is dependent on the amount of electrons, the amount of kilovolts, the probe current that you introduce your sample, and also is dependent on the density of your sample. So you have a low density sample, the penetration of the beam will be much deeper. And if you're a high density sample, your penetration will be a little more shallow. So as you see at the bottom, you see that you have a 1 kilovolt beam current, which is a much smaller beam volume as get generated. Then you get into a 5 kilowatts, slightly bigger, and then your 20 to 30 kilowatts is a much bigger beam volume that penetrate into your sample. So electron beam versus sample interaction. Okay, so sometimes if it's depending on the type of sample, again, if you have a high kilovolt beam current that introducing, and it's, say for instance, it's a high density sample, the penetration will be more shallower, and then your beam interaction volume will also be smaller. So if you have a very sensitive beam sample, a biological sample, or polymer, or any particles with light atomic level composition, and you introduce a 20 kilovolts, you will have a much bigger interaction into your sample. But if you want to see only on the surface of your sample, and you don't want to cause any beam degradation because of the kilovolts that you introduce in your beam in the sample can't withstand the high intensity of the beam current, then you must drop your beam current to a much lower current, and then you will introduce a much smaller beam volume, and you can then see, and the beam will then project a much surface topography on your sample or morphology of your sample. So these various signals then can be detected, and that will increase with an increased accelerating voltage and decreases with an increasing atomic numbers. So SEM versus FEC SEM. So you get different types of SEM, as I said in the previous slides. You get your field emission SEM, which have a field emission crystal, and you get also your normal entry level SEM, which uses a normal tungsten filament. And as you see at the bottom, we have examples of these filaments, and these filaments project the quality or high resolution that you can generate. So the first one is your lab 6, which is then your higher contrast than that of a tungsten wire filament. And the tungsten wire is you can go image down to macroscale only. And then you get your field emission tip, which is a crystal, tungsten crystal. And that is where you can generate down to nanoscale. So if you have images, samples that you see in nanoscale, you have to use the field emission tip or field emission SEM to generate those high resolution images. So comparing a SEM with a transmission electron microscope, so you'll see that the beam is much in the transmission electron microscope much broad and static. In the scanner electron microscope, the beam is more focused with a fine point, and the samples then scan line by line. The voltages needed in the transmission electron microscope, your voltage is much greater, from 60 to 300 volts, where in a SEM, you can go to only up to 30 kilovolts. Okay. The interaction, the specimen must be thin in the transmission electron microscope, ultra thin specimen. And then for the scanner electron microscope, you can actually introduce any type of sample into your SEM. If you have environmental SEM, you can introduce a sample that is even not coated. You can introduce a sample that didn't go through a drying process. In a normal SEM, FEC SEM, or any SEM that is not variable SEM, you must dry your samples first. But the sample preparation comparison that of the transmission electron microscope is much quicker, faster, and cheaper. So you can get very quick signal, very quick images. You can get very quick composition from your scanner electron microscope than that of a TEM, where a TEM requires a much longer sample preparation. But if you get certain samples, if you have particles in a liquid form, which is then something that you can then introduce also in the transmission. You can just drop your sample onto a STEM grid that can get introduced into a TEM and also in a scanner microscope with a STEM detector, and then you can then view your particle sizes on the grid there. So in the TEM, the electron beams pass through the sample. Therefore, your sample must be very thin. And in the SEM, the information is collected near the surface of the specimen. So transmission electrons are then collected, focused by the objective lens and magnified and create a real image on your transmission electron microscope. And in your SEM, the beam is then scanned along the surface of the sample to build up the image. This is where Alicia will take over from me, and thank you very much for your attention.
Okay, awesome. Thank you so much, Madelaine. Yeah, so we said we're just going to have a quick look at TEM because we can't really exclude it from the polymer science aspect of the talk, because it's still very useful for any type of nanomaterial or polymer material, the investigation thereof. Most often though, TEM is commonly used for biological samples. Or samples that are more squishy, to say that for the lack of any other word, that contains moisture that needs to be prepped in a certain way to have ultra thin sections, like Madelaine mentioned. In this picture here, we have indication of what the process looks like for transmission electron microscopy sample preparation. So you first begin with the sample itself will be embedded in some sort of resin. Usually you can go through a few other processes like, well, it has to go through fixation, which I can go in a bit more in detail later. And then some staining to cause contrast between your sample and whatever you're investigating within your polymer. And then it will go normally through a microtoming, ultra-thin microtoming sectioning. And that section will then end up on the grid. And then this grid is usually a form of a copper grid, but there are many types of TEM grids available, which I won't go into because that is a big, a massive amount of information all at once. But yeah, you're welcome to have a look at it yourself if you need more investigation around that. But most commonly, it's just a copper grid that is used. So the main advantages of the transmission electron microscopy is the ability to reach very, very high magnification. So we're talking about nanoscale and still acquire high resolution images. Unfortunately, with SEM, there are some limitations in terms of how far you can go with the magnification and still get high resolution images. So in some cases, it will be necessary to switch over to transmission electron microscopy if you need to go there with very, very small material. So and then also is used for, most commonly used for examining structure. It can be used for chemical composition analysis as well, although that setup is very tricky and you'll need to you need to find a proper SEM instrument that can have the ability to do EDX while doing STEM or transmission electron microscopy. And then, yeah, so that's most commonly you'll look at a sample. If you're working with a polymer, it will be sometimes in a biological field, or if you're looking for nanoparticles, nano types of nano whiskers. I don't know if anybody here works with chitosan or chitin, but in my project, I had to establish whether I was successfully making chitin nano whiskers from chitin. So that's where I needed my transmission electron microscopy. So yeah, so that's most commonly biological, medical, material. It can be used for geological, but that's not very common. And then very, very important for technological studies. So yeah, and I think just to cover the rest of it, I think I've covered most of that. So I just want to show you the next slide. Just a quick look at what the TEM looks like. It looks a bit different than a SEM. I've actually linked this YouTube channel, and I will also put this link in the chat afterwards. Please feel free to visit this YouTube channel and also this microscope training simulator, because it is magnificent and really gives you a good insight on how to work with a TEM, especially in polymer science, where you most likely, if you are studying in that direction and you're looking at diffraction patterns, then this will be a very, very helpful tool for you to understand how diffraction patterns are acquired in many types of polymer materials and how it works. Unfortunately, I don't have the TEM, we don't have a TEM at the Central Analytical Facility we used to have, but otherwise I could have showed you some live images or so on. But this is a really useful tool that I find will help many students out there that needs to work with this in particular. But yeah, so what Madelaine mentioned was that the main differences between a SEM and a TEM is that the TEM, the electrons go straight through your sample. It's transmitted straight through your sample, while with SEM, it's scanned all over your sample and it's mostly giving you the surface analogy. So that's that. Now, I don't want to exclude CLEM from this talk because it's also such a useful tool for polymer science, although going in depth once again is an entire hour's talk on its own. So I'm also just going briefly over it. But correlative light electron microscopy is a very, very useful technique. It combines the analysis of immunostaining, usually for biological molecules, but also it can be in combination with, like I said, polymer materials, depending on your study. If your study is a mixture of the two fields, then that's very useful to have CLEM. So yeah, so it's basically also an ultrastructure feature analysis, and it can show you many different types of interactions with your material and the biological aspect of what you're doing with your sample. I can show you in this next slide an example from Dr. Mariki Lutz and Melissa. They were working on chitin nanowhiskers engaged with EVOH, which is a polyethylene vinyl alcohol fibers. They electrospun these fibers, and then they incorporated silver nanoparticles. And these they stained, and then they wanted to see the distribution of these nanoparticles within the fibers. And that really was only made possible with using CLEM. So yeah, so the efficient characterization of the distribution of the antimicrobial agents, which is the silver nanoparticles, were investigated within these polymer matrix, and then they could see exactly how well does it distribute across the fibers. Is it uniform? Is it clustered or agglomerated? And where is it interacting? Is it interacting with the fibers itself, or is it interacting on the surface of the fiber or in the interior of the fiber? So that was very helpful information for them to use the CLEM. They also incorporated SEM, and then they used EDX mapping to get this effect that you can see here in the image on your right. Yeah, so they looked at particularly the carbon distribution, and then also, like I said, the silver distribution on the fiber mat. And the mapping and the EDX mapping also helped show that. So they used CLEM and they used SEM, EDX, and all of that in collaboration gave them a very good overall view of what they can expect and how well their silver nanoparticles and fibers performed. So yeah, so here they use the correlative light and the electron microscopy in combination. On the top right, you can see the SEM image, and then the red is the chitin nanowhiskers, and the blue is the silver nanoparticles. So B, this one here, is the backscattered SEM scanning electron microscopy image. And then C here is the elemental mapping that was showing the carbon in purple and the silver in cyan. So you can see a great overlay of the two. The carbon is the fibers, and the silver is obviously now the light blue. So you could see that wherever the fibers were, the silver was. So they were definitely correlating and adhering to each other. And yeah, and the confocal microscopy was shown in D, also establishing that. So that's just one example of polymers with CLEM. There's many others, so you can please have a look. And there's so many research studies available. And if you want, I can also share some more afterwards. So just to talk about the sample itself, because that is the most important thing. If you do not do a proper sample preparation, no matter what you do in terms of SEM, TEM, CLEM, whatever, if the preparation of a sample isn't done correctly, then there will be no image for you to use, unfortunately. So many people underestimate the steps for the sample preparation step, and they think that it's something they can shortcut or do quickly, and unfortunately that will be very costly. So in terms of the sample itself, for this talk now, specifically polymer science, you have a variety of sample, and because polymers is so diverse, it can be present in many types of fields. So your specific research or study might be not just biological, or it might be integrated with engineering, chemical engineering, or it can even go into geology, or perhaps it's going into more biochemistry field, or it's so diverse. So your sample can also then vary in terms of size. So it can be a very large sample, it can be powder, it can be nanoparticles, it can be fibers that are very tricky, or it can be some sort of moist hydrogel. So all these samples, different types of sample prep will apply. In the most general sense, scanning electron microscopy will ask you to have a stub, just a normal aluminium stub with double-sided carbon tape. and you put your powder on there. If it's a dry, straightforward sample, then you just put your sample on there. If you're looking at the surface, that's as straightforward as it goes. You might need to coat it if it's not a conductive sample. And that's usually coated with gold or carbon, but yeah, I'm jumping the gun. I'll go on to the next slide. So that's just very straightforward. But yeah, so in terms of the analysis, if you're coming with your sample, you need to have the type of analysis that you have in mind. You need to speak to the analyst before starting the preparation of the sample. So if you're coming with your sample and you are interested in chemical composition, then you need to take into account that when you do the sample preparation and you might be interested in gold in your sample, then you should probably not coat with gold, which is one of the things we use when we try to make our sample more conductive. So we have carbon and we have gold coating. So then you already need to start making decisions like avoiding the gold coating so that you can do chemical composition analysis of your sample that contains gold. So you don't want to cross-contaminate and then destroy any chance of getting a semi-quantitative analysis. So in this case here, I'm just showing you what I'm talking about when I'm saying backscatter detector and secondary electron, as we talked about it earlier, and then correlative light, and then photoluminescence, sorry, and then scanning transmission electron microscopy. So these are the four main things that we often work with in terms of if it's applicable to polymer science. It's not always. So photoluminescence is not necessarily used for polymer science, but I just needed to show you that because it is a very useful tool that we often work with. In this case, you can see the bottom left corner where the photoluminescence is shown. These are zircons that are used for carbon dating and so on. And you can see the zoning very clearly, and that's very important for geologists. But the top left and the rest of it, secondary electron and scanning transmission electron microscopy is most commonly used for polymer science. So the BSD is where we will probably start most commonly for any chemical composition analysis or any high contrast phases that you need to see between your material. As Madelaine mentioned, the atomic number differences in your sample will show a very high phase contrast as the material varies in composition. So, and then on your top right is just secondary electrons, which shows us surface topology and morphology. So that's very, very useful when you want to look at any interesting features or textures on your sample surface. And then, yeah, the scanning transmission electron microscopy is something we can do, not TEM, but it's still something useful that's very closely related to TEM, that can show us nanoparticles in high resolution. All right, so there is just a few things when you're doing SEM that you need to take into account. If your sample is correctly prepped and there's no additional external factors that are causing problems with the imaging, then it's mostly a signal to noise ratio that needs to be fixed. So you should definitely also just make sure that your contrast levels and your brightness levels are correct, and all these things are according to preference as well. So mainly, if you want to have a crisp appearance, it's just very important to have your sample firstly very conductive, and then the rest of it will just be altered on the SEM software according to preference. So here we talk about the acceleration voltage via the specimen type. So yeah, in theory, an increase in acceleration voltage will result in a higher signal and lower noise in the final image. But the situation is not so simple. There are some disadvantages. So reduction in structural details of the specimen surface in secondary electron mode increases the electron buildup in the insulating sample, and it causes charging. Now, charging is a very, very common problem in samples, and can be caused by many things like moisture buildup if the sample wasn't properly dried, Also, if the sample is moving, so like for fibers that are very light and not perfectly adhering to the double-sided carbon tape, so that can also cause movement and then charging in that effect. And then, yeah, so increased heating and the possibility of specimen damage can also occur if your sample is very sensitive to the beam, unfortunately. So with a higher acceleration voltage, the electron beam penetration is greater and the interaction volume is larger, but therefore the spatial resolution of the micrograph created from those signals will be reduced, and the number of backscattered electrons will increase. For secondary electron imaging at the typical voltages, BSEs can enter the secondary electron detector and degrade resolution. So what basically is said by that is that if you want to look at the surface, then you just need to adjust your acceleration voltage accordingly. So we don't use we don't need to use high kilo electron volts. We can use 3 to 5 will be most common. And if you need to look at that backscatter electrons for chemical composition or for high contrast, for that phasing that we talked about earlier, then you can go for higher. So usually then around 20 kilo electron volts. And then the other thing that's very important to get a high quality image with SEM is the spot size. Now, this is, okay, so the size, this is called the cross-sectional diameter that the current of the beam makes on the surface of the sample affects the resolution of the image, the number of electrons generated, and then also therefore the graininess. And then at low magnifications, we use a larger spot size than at higher magnifications. So in this image, you can just see it a bit more clearly what I mean by that. So it's also very important to note that the speed of when you're scanning your sample, the speed will also affect the graininess of your image. So the slower the scan speed, the higher the quality of your image will be once you save it for use in the article. All right, so here is just an indication of what I mean with the spot size. If you can see the effects on this image from left to right. So the image is taken at the same magnification and kilovolts and working distance and everything, but using a different spot size shows these effects. The difference is causing the blurriness. And yeah, so the spot size on the far left is 60 and the spot size on the far right is 17. So yeah, there was like a variation from 60, 50, 40, 30, and then 17 at the very end. The way the spot size is reported depends on the make of the machine. So that also varies from software to software. And the images of a cross-section through carbon fibers from a polymer. In fact, that was embedded into a polymer. But yeah, so you can see the effect that this has is very, very important. So you need to, from the beginning, have your settings correct. And it's very important to maybe, if you're going into a research study where you're going to work with the scanning electron microscope a lot, make sure that you make a note of those settings so that even after a few months coming back to the same, you have those settings and you can recreate and reproduce the same images. Sorry. So yeah, here I talk about the scan rate, which is also correlated to the signal to noise ratio. So very, very obvious, the slower the scan rate, the higher the more electrons is collected by the detector, and then it just produces a better quality image. And then the image quality of the SEM is limited by the spot size and the ratio of the signal produced by the electron beam to the noise imparted by the electronics of the instrument in the displaying of the signal, so the signal to noise ratio. And noise pulses are derived from such sources as beam brightness, the condenser lens settings, which is the spot size, and in the secondary electron detector. And so, yeah, and then may also impart some graininess in the appearance of the image. So when the SEM is set up to high resolution imaging, it will often have a very low signal to noise ratio, and then that will appear grainy. So that's something that you just need to slow down that scanning speed to remove that graininess. And then with the depth of field, that can also vary depending on what type of SEM you are using, but mostly the working distance affects the depth of field. And that's just the distance between the lens to the sample, and that can be manually controlled. But in some cases, the working distance is set to a certain height because of the optimal distance between the sample and the detector, for especially for EDX analysis, where we're looking at the chemical composition of the sample using the backscatter electron and the backscatter detector. So that's sometimes the working distance is set to a specific setting and that can't be changed. Then you'll need to use focus. But yes, mostly the depth of field. If you want to increase that, you just enhance the working distance. Yes, I think that is about it. So the role of a sample height. So yeah, sample height or working distance refers to the distance between the bottom of the SEM, as I've mentioned, and the column. So the lens on the top. Within the sample chamber, the sample stage can be wound up closer to the end of the column or drop down. So that is the Z that they are talking about. Usually it's with a toggle or with a joystick that you work that. And the shorter the working distance, the smaller the diameter of the beam is on the sample surface. So when possible, the working distance is kept at 10 millimeters or smaller for high resolution imaging. And the working distance itself is also a big stress factor for many students or people that are new to the SEM, because if this working distance isn't correct and you get too close to your sample, there's a potential that you can bump the lens into the sample, thus destroying your sample or damaging the lens, which is going to be a very costly mistake. So usually there's also a working distance limit set by the software to prevent that from happening. And then now going back to sample preparation in a bit more in depth, specifically speaking now for polymer materials. So most polymeric and nanomaterial samples will be mounted in the standard method, as I've mentioned, with the aluminium stub and the double-sided adhesive carbon tape. Aluminium tape can also be used, especially if you're looking specifically at carbon and you're trying to get more than just a semi-quantitative analysis. Then you can use that to avoid the carbon tape interfering with the chemical composition analysis. So the beam might pick up the carbon behind your sample. So, and then the samples are typically coated with gold or a combination of platinum and gold or carbon using sputter coating. And this will depend on what you're looking for in your sample. If you're simply looking for images, then gold will be perfectly fine. But if you are specifically looking for gold in your sample, then you need to avoid that, as I've mentioned, and maybe choose another coating method. So yeah, this enhances the conductivity of the specimen and allows the electrons to find a stable pathway as the sample is being scanned with the high intensity electron beam. It is important that the surface of the stub and the carbon tape should be clean to avoid any contamination or artifacts. And then working with a hygroscopic sample, which is a sample that absorbs moisture from the air very quickly, such as powders or even fibers, the sample need to be placed in an oven, or if it cannot go into an oven, if it's sensitive to any heat or temperature, or you're specifically looking at how temperature will affect the sample, then you don't want to interfere with that, then you can use a desiccator to dry your sample thoroughly, or to keep it at least away from any moisture if it's already dried. So here's just another image of what aluminium stub with carbon tape will look like. So this is now the interior of a SEM, not ours, but it's just a photo of the interior of how you would mount the sample into a SEM before it gets loaded into the chamber. Our SEM has a double chamber where, like Madelaine said, the chamber is constantly under vacuum, so the vacuum doesn't get broken. And then we have an exterior storage chamber that the sample goes through to keep everything under a vacuum, which saves a lot of time, and it just keeps the SEM from any contamination. And then, so this is a photo of a carbon and a gold coater, mainly what they would usually look like. So this one on the right is currently sputter coating. Usually the coating will occur for a 10 nanometer layer. Some people go for a thicker coating, but very rarely is it necessary to do a thicker coat than 10 nanometer for carbon or gold. But yeah, this can be adjusted accordingly depending on your sample. For many cases, if the sample is charging and it's already gone through a proper drying phase and is still giving issues, then another coating will be suggested to avoid that issue. So examples of SEM and the application of this on polymers and nanomaterials will be mostly, most commonly people will look at polymers and the failure of these, or the fracturing of polymers. So in one of my studies, when I was just beginning with my postgraduate journey, I worked with tensile testing on polymer plastics, where I was trying to introduce chitin nanowhiskers as a filler to potentially enhance the strength of these polymer plastics. But yeah, so that was what I was looking for. I firstly needed to see whether the fibers that I was electrospinning was evenly distributed in this polymer plastic, polypropylene and high impact polypropylene specifically, and also linear polyethylene. So that was where SEM was very useful, because I could see that the fiber was evenly distributed in the polymer film after the melting process. And also, when you do the tensile testing, you can evaluate the fracture. So there are many types of fractures, as most of, I'm sure probably a few of you know. Crazing and shearing is mostly the most common ones, and that can very easily be seen using SEM. And this is just a little bit more in detail with tensile testing, as it can cause necking and then the fracture, and then that can be put onto the SEM stub on a 90-degree angle. So you can even visualize that fracture from the top. So you can put your sample in on the aluminum stub in any way that you are interested in on the area that you're looking for. And we do, and there is, like I said, that's why the SEM is so amazing, because you've got your basics, but then you've also got the technology that is growing and constantly being adapted to researchers' needs. So there are now 90-degree stubs where you can easily angle your sample for the way that you want to visualize it, for the cross section and so on. So yeah, another example of brittle crazing and ductile fibrils and what they look like under SEM. Also credit to David Robertson. He has a YouTube. You're welcome to follow that link and check out more of that, where he describes the exact the description of what you're seeing here for anybody that are focusing on this type of research regarding polymer science. And then for another type of use that's most commonly used for polymer science is semi-quantitative chemical composition analysis. For the reason why I say semi-quantitative is because it's not always exact. So there are other types of characterization methods that are a bit more highly accurate. So because you're looking at such a small portion of your sample in SEM, if you want to have a broader, more accurate view of your entire sample, it might be better to go for NMR, FTIR, HPLC, even VSC or field flow fractionation. So yeah, but most students would just like to know whether the material that they are introducing to their sample is present, was successfully introduced, or they may be looking for contamination, or perhaps they're just looking for the combination, whether it's present, or just to identify what their sample is currently looking like. So yeah, so in some cases the EDX is much faster, easier, cheaper, and gets the job done that they were looking for. So yeah, most commonly these are the most used for polymers. But be aware that if your sample is just a plain polymer that's hydrocarbon based, like carbon, hydrogen, and oxygen, then unfortunately that will not really show much information, unfortunately. So it could be possible if you want to compare maybe PVC to PE, polyethylene to polyvinyl chloride, then there will be some definite differences because of the chloride present in the PVC. But if you're comparing polypropylene to polyethylene or something that's just hydrocarbon based, unfortunately, you might see some differences in the carbon and the oxygen ratios, which can help you distinguish between the two polymers. We have done that before, but it's very, very tricky, and FTIR would be much more equal to the task if you want to do that type of analysis or comparison. So yeah, and then obviously the most common use for EDX is also the evaluation of the contamination. So here you see fibers that are not necessarily contaminated, but they were introduced to water, and they needed to be evaluated to how much do they filter, can they be used as a filter membrane, etc. And in this case, on the left was also a type of a membrane that showed some contamination and so on. And then here you can see this was actually on the left. The artifacts that you can see here embedded in this polymeric material is from a dental chew toy that was manufactured from polymers for dogs. So there we could see some very interesting different types of materials compressed together to make this chew toy for dogs. And then on your right, just fibers as well. Once again, most commonly, these fibers are evaluated for contamination, any bacteria that might be adhered to these fibers, etc. All right, and then here is just a indication of what a polymer material looks like if it's containing various different elemental composition. So there's like titanium showing up and iron and so on. So that's very useful for the student because he wanted to see whether his sample was pure or whether there was some a mixture of things in there. Many people use the EDX for electrodes or composite polymer materials that are not completely pure. All right, so now also the other type of use for SEM for polymers is particle size distribution analysis and porosity measurements. As you can see here, the fibers can be measured. There's a free software that many students, is very popular among students. I'm sure everybody knows about this maybe, but ImageJ, and that is very, very useful to measure small porous materials like this and multiple pores. And then you can also get a good statistical overview of your sample in terms of fiber diameter, pore diameters, and just the standard deviations between those. So, but yeah, so that's also a very useful tool for with SEM for polymers. And then obviously the morphological and topological information, very, very important for materials like these. On the left is one of my chitosan sponges that I was making during my PhD. And it's just a bunch of nanoparticles compressed into a sponge-like material, which looked like styrofoam. And that was used for the treatment of heavy metal in water. And we wanted to see the porosity. We wanted to see whether there was an even distribution of this particles. And yeah, it's not necessarily nanoparticle anymore, but yeah, so now it's more like a mesoporous sponge. And then on the right is just also I think it was a COVID mask or something, and they wanted to measure whether there was any pores between these fibers and how well it was actually protecting the person wearing the mask. Yeah, so that's it. I jogged through it very quickly. I hope I didn't keep everybody too long. But is there any questions? You're more than welcome to ask.
Well, great. Thanks, dear Alicia.
No problem. I will quickly add that.
Please, Dr. Said. Dr. Said.
Thank you very much for the great lecture. Could energy dispersive X-ray EDX combined with the scanning electron microscope SEM be good? Then we use SEM alone. The second, although clear difference between TEM and SEM are required by many reviewers of both, is this necessary for the surface measuring? And what type of nanomaterial or polymer cannot SEM or TEM be used for obvious explanation? Thank you so much.
Well, I'll start with the last question. So most, like you see, I maybe, I kind of on purpose excluded hydrogels from this talk because they're the most troublesome, unfortunately. For SEM, they are very, very troublesome to prepare without changing the composition, changing or introducing artifacts, or trying to take them as far away from their natural state. So I would definitely recommend TEM for that, and for anybody that ever wants to. But that really depends on what you're looking for in your SEM, in your hydrogel. So if you're looking for something specifically, just if it's like a pure sample, maybe it's possible to use SEM. But yeah, that's one of the ones that are anything that has moisture that cannot be easily removed from the sample is very troublesome. Also, something like a wax that is very susceptible to beam and melting under high temperatures, because the electron beam is so strong, it will possibly damage the SEM as well as the sample. And then you were asking about the EDX in combination with the SEM, correct?
Yes, we use sometimes sometimes SEM with EDX it is very good for the clear result for the surface analysis for some polymer and nanomaterial metal compound. It gives the clear ratio of each element for a polymer, such as carbon, nitrogen, oxygen, hydrogen. It gives a clear number of atoms for each polymer. And the other, it gives the signal of the surface that can be in nano or structure 2D, quantum dot, 3-dimensional, and so on.
Yeah, no, I agree with you. I feel SEM in combination with EDX is the best possible way to do a study in terms of polymers, because like you said, you can see the surface and you can see the different types of morphology maybe on your surface, and then you can actually concentrate on each different area. So if the surface is looking very heterogeneous, then you can distinguish between those heterogeneity of the sample by using the EDX. So you can do spot analysis, or you can do like an entire area. So you can get composition of the chemical composition of the entire area, and then also identify each different little particle or grain or anything that looks a bit strange, that doesn't look like it's supposed to be part of the matrix or whatever. So yeah, I do agree with you that is definitely a very good combination, especially if you have those options of, you can do mapping, which is what I showed with the CLEM, where you can see the elements distributed in different colors. So you can see how they're associated as well. So let's say you have like an oxide, and you can actually see the oxygen overlaid with the other element, let's say silica or whatever, and then you can see that that's a silicon oxide or so on. So that's a very good way of identifying any contaminants or artifacts, or just simply the matrix that you're working with. Yes.
Thank you.
There was a third question, but I hope we answered that.
Thank you so much.
No problem.
Thank you, Dr. Said. Modo? You can open mute.
So I just wanted to ask, I've been training with the high resolution 10 recently, but I seem to be struggling with the Z heights like most of the time. So I just wanted to know if there's any tip that you can give me when I'm dealing with the HR with the height adjustment.
Yes. I think if you're just doing, are you just doing scanning electron microscopy or are you doing transmission? Sorry, I just wanted to make sure. But if you're doing scanning electron microscopy, the Z will definitely affect your imaging. So if you're, I know that is usually mainly a big problem with the sample type as well. So if your sample height is different as well, then you have to adjust accordingly. So if it's a big sample, then unfortunately you'll have to increase the working distance. But if it's a flat sample very close to the stub itself, then the distance needs to be decreased between the lens and your sample. And then what also should be taken into account is that you should work with the correct the acceleration voltage. So if your sample is a very sensitive sample, maybe start with 3 and go up to 5 kilo electron volts. And your probe current is also very important. So even if your Z is correct, just make sure that those settings are also adjusted. But if you still struggle with the Z and the focus is not working, then if there's a technician that can help you, it's usually something to do with the alignment of the beam. So there's astigmentation and the gun alignment that needs to be correct as well. So no matter how much you fiddle with the focus and your sample's just not working out, the image is still looking pixelated and blurry, then it's usually something to do with the alignment of the SEM. Which they talk about it, they call it wobble and stigmation. So those two factors are also probably what's bothering your image at the moment.
Does the gold or affected the image quality?
Say again, sorry?
Does the gold or carbon coating sample affect the image?
It can. If you are going for a very thick coat, then you might start seeing the nanoparticles of the gold on your sample. Yes, that can definitely happen. If your samples also maybe fell over on top of the gold coating sample holder, some of the actual gold that was coated on that falls onto the gold coater might become attached to your sample. So then you'll see big shards of gold on your sample. So that's also, cross-contamination that can occur. So that's why you need to always be very, very careful when you work with your sample and try to, lower those risks. But in general, a 10 nanometer layer shouldn't affect that. You shouldn't be able to see that on your sample, no. Oops, did I move something away? Should I stop? I'm going to stop sharing my screen.
Thank you, Dr. Sinan. Many of the audience.
Yeah, we would like to thank you and Madelaine for accepting our invitation and also for your insightful presentation.
Okay.
So I just have a quick question for you.
Okay.
Is some for the printed electrode on substrate with any substrate, if it's like aluminum substrate or the PEN sheet, is it possible to measure the height of the printed electrode? I know it's possible through the AFM, but I'm not sure of using the SEM. This is one thing, and I know with the SEM we can like see the morphology of this film. Yeah, so my question is about the height of the printed electrode. Is it possible to measure it? You are muted, Alicia.
Sorry. I didn't even notice. It's a very good question. We did actually try that with something. We were doing laser ablation ICP, and the person needed to measure the depths of the craters that was being inflicted on the sample. So we actually used the Z, the toggle, and then quantified the height or the depth of this crater using the Z itself. It's not a common tool used for that aspect because it is linear and you only see from the side. But because we could see from the top view when you're using the SEM camera, the detector itself, we could actually so it's also not very accurate, but you can see once you focus the bottom and you can see the bottom in complete focus, then you can take that Z, let's say it's like 10 millimeters, and then you zoom out using the Z only. And once you can see the crater and it's in focus, then you can take that Z, and then the distance between those two Zs will be the depth of the crater. But it's very crude, it's very rudimentary. It's not exactly what it's supposed to be used for. But I do believe that if that's just, you just need to acquire, just like a short, easy way of just a quick measurement, then I could suggest that. But if you need to be very, very accurate and it's very important for the study, then I would not suggest doing that.
Okay, I see. I think it's possible with the DICTAC one. We can measure the height.
Yes, it's doable.
You did mention that it's possible to know the porosity of the polymer or the hydrogel. Is it possible also to know the porosity of the printed electrode?
If there's any pores and it's above, it's nanoscale, but it's it's possible to see it with the SEM, then I'm sure that you'll be able to measure it using the software that I've mentioned, ImageJ. But there's also many other types of software that are actually a bit more user-friendly. So, but yes, I would assume that you could be able to measure the porosity.
Okay, great.
Yeah, but it's better to use a software, especially if you're using statistic. You want to see the standard deviation and be very thorough with the average and all that stuff. So
yeah. Okay, great. Thank you.
No problem.
You are muted, Dr. Athir.
Mr. Amir Amari, if you have any question, please. I have just one question, Hito, about scanning microscope technology. And this examination considers basic or attributable to research.
Sorry, I think your audio.
I think my is not good.
There is some lag.
Okay. In chat, the question in the Mr. Amir, is the examination considers basic or attributable to the researcher?
If someone can maybe repeat that question, I couldn't hear it out properly, unfortunately. Sorry.
Yeah, I'm just trying to find it actually.
Okay, no problem. So I heard every third word. I think there's some issues with the internet.
Is this examination considered? I found it. Is this examination considered basic or attributed to the researcher?
What type of examination are we talking about?
I'm not sure. I think they mean like the SEM or something else.
If it's the chemical composition or just in general, it will be very specific to the student or the researcher and the type of analysis that he or she wants. So
he is asking about the SEM.
Okay, that is why I feel like we can talk for more than 1 hour about this topic, because the SEM is just such a growing technology. There's so many types of SEMs. We're talking such basic. So in terms of, we didn't even really touch on the resin embedding preparation and ultra-thin sectioning. We're using a microtome to do a serial block face, which gives you a 3D animation of your sample using machine learning and software like that. But in general, if you're coming with your sample, the best thing is to talk to the analyst exactly about what your aim, the main aim of your sample is, or the analysis is. So if you're looking for chemical composition, then there will be a certain type of sample preparation for that. If you're simply looking for topological, morphological surface analysis, then there will be a very simple, most likely very simple preparation for that. And you'll maybe just use SEM instead of SEM in combination with EDX. So yeah, it's very specific to each researcher, and can be modified, and the sample preparation can even be modified depending on the sample itself and the research that needs to be done with that sample. So yeah, that's why I think SEM is so interesting, because it's never just one thing and it's never just the same.
Riam? Riam, are you Riam Abdul Zara? Please unmute and you can ask your question. Riam? I think the image is free. I think it's not
Yes.
free application. Image.
It is a free software, yes. It's very popular, used under the students here in Stellenbosch. I'm not sure how popular it is anywhere else, but yeah, we use it a lot.
Maybe in next 2 months, 3 months, need to another lecture from you about imaging.
I could do that.
This is a good chance to ask.
No problem. Hello.
Thank you. I would like questions you, please.
No problem.
Okay.
Does the gold or carbon sample affect the image quality or no?
Sorry, does that? Just repeat that question, my bad.
Does the gold or carbon image effect of the image sample quality or no?
Oh, yeah. So I think we had this question earlier where whether the gold was affecting. So the same with the carbon as well. So the thicker the coating of the sputter coating on the sample, the more likely it will affect the image of the sample. But Madelaine, you have a geological background as well as botanical background, and she works with carbon coating a lot. And I think the only time when carbon coating really affects the sample or the imaging when you're under the SEM is when the sample itself, the thin section or whatever you've been working with, isn't cleaned properly or dry, especially if it's not dry, before you do the carbon coating. So the way the carbon adheres to the surface of the sample will be affected, and that will affect the SEM. So you will then see charging, etc. So yeah. Sorry, that's a long answer to say yes, it might, if it's not properly, if the sample isn't properly prepped. But in terms of the layer, it's too thin to really have an impact on what you will visualize under the SEM.
Yeah, I also wanted just to add in there. So basically, the first question is why do you think the coating will affect the quality of the sample? Normally, the coating is basically helping to improve the resolution quality on your sample. If your sample is not conductive, you definitely need to make it conductive by adding a conductive layer using either carbon or metal, or gold or palladium, or gold palladium. And there was another question there you should ask is like the type of coating. When do you choose what type of metal to add to your surface? So that will also help you with the resolution you're looking for. For instance, if you have a very high resolution image you need to generate, you need to add maybe a much more expensive type of metal like your platinum, which will give you a much higher resolution, and that's going to affect the particle analysis that you want to look at. Say, for instance, you go to much nanoscale images, you won't see the atomic layer of the platinum so clearly as you would see with gold. So you can definitely have to look at what are you looking for. Are you looking at high resolution nanoscale images? Then you would prefer use rather platinum layer, conductive layer in your sample. If you just want to look at nanoscale, macro scale, then you can use gold, which will improve the resolution of your images if you have a non-conductive sample. And if you have something that's very light atomic sample, you can also use your carbon. So the thickness of your carbon is very important. If your carbon thickness is not, or your sample is not evenly thick, spread, the carbon is not evenly spread across the sample, and you expose certain areas is not completely coated, that will cause some electron get some absorbed into your sample, and that can cause the artifacts and the charging that you see on your sample. So it's very important, if your sample is not flat and even, you maybe have to consider to introduce your sample to certain angle to make sure that all the different grooves and pores and holes get coated properly, so you have a good conductivity across the surface of your sample. So so I don't think any coating will affect the resolution, but will improve the resolution, definitely.
Also, Alicia, for me as polymer, we take the hydrogel polymers and explain the nature of the surface as roughness or soft, and explain the pore size which found it. What can we explain other for this thing?
Sorry, did you say like what other methods can you use to?
We focus just on the surface roughness and pore size. So what the things?
That's for hydrogels.
Yeah.
Okay. Well, hydrogels, like I mentioned, is not my favorite sample for SEM. But I think it's possible if you want to do chemical composition analysis, it might be possible. Since you're not focusing on the structure of the sample anymore, it is possible to then dry the sample accordingly for the chemical composition analysis, because obviously you've already seen the surface, you know what the surface looks like. Now we can destroy the sample, not destroy, but disrupt the surface just to get it into the format we need for EDX analysis. So I do think chemical composition is possible for hydrogels. It's just unfortunately, I think you might lose that the morphological aspect of your sample might be disrupted due to the sample preparation that's needed for the SEM. Yeah, that's about, I think even you can use, you've probably done scanning a lot of TIM with your hydrogels as well. I'm not sure if you did, but yeah, that's most commonly what's used. And I know there are transmission electron microscopes that can also do EDX. So that is an option for you as well, the combination of those two. Also, cryo-SEM, you can use liquid nitrogen to spare your sample any disruptive sample preparation. It freezes the sample as is.
Yeah, we did actually. We use the cryo-SEM. Yeah.
All right. Yeah. So that's also a very useful. I love that instrument. Is very interesting, and the technology around that is ever growing. So, yeah, that will be the best for your sample.
Right. Also, many of audience, Alicia, asked me to, if available, to share the PDF lecture. So if we could it to me and share with, very beautiful.
All right. Would you like me to send it to you, or
should I? My email. To my email.
I will do that. I will do that. Okay. All right then.
Dr. Maan, Dr. Maan.
Hi, everyone.
Hi.
I wanted to thank you about this talk. This is first. Actually, my question about the polymer and the TEM. If we use the coating for organic polymer on the surface of the polymer, definitely we can use the TEM to characterize this polymer by measuring the size for nanoparticle as a general. But my question, could we determine the thickness for the coating organic polymer on the surface without measuring the size of nanoparticle using the TEM?
I do think, especially for TEM, you'll definitely be able to do that. Are you talking about the spatter coating itself, or the coating of the sample, the natural?
Yeah, for example, before we doing the coating, we can measure the size for nanoparticle using the TEM. But
Yes.
after we doing the coating for the polymer or organic polymer materials on the surface of nanoparticle, could we measure just the size for the thickness for the coating layer?
Whew. It might be tricky, but I do think, Madelaine, you should help me with this one. But I'm pretty sure that it might be possible. However, usually the thickness is already in a precise measurement when you're doing the coating. So if it says 10 nanometers, then it usually is exact. But if you wanted to make sure, if you're not exactly sure whether the accuracy of your coater is actually set to 10 nanometers and there might be some discrepancies there, then I do think it might be possible. But what do you say, Madelaine?
Depends on what type of coating you add to the sample. If it's a metal coating, if it's a metallized coating, you can definitely measure the thickness. So if you use a carbon coating, that will be difficult. But definitely with a metallized coater, you can definitely then you can use different modes in your transmission electron microscope, where you different detectors, and you can see the like in the STEM we use the HADDF, where you can measure see basically under contrast differences, and then based on the contrast differences, you can then measure the thickness.
So could we compare between two measuring by TEM before we doing coating and after we doing coating?
Yes, you can definitely do that with the transmission electron microscope. Yeah.
Oh, okay. Thank you very much.
Sure.
No problem.
Thanks, Victor. Okay.
Thank you.
Great. Thanks to Madelaine and Alicia. You are very welcome with us. And I'm from now, I tell you, I ask you to make the training lecture for MJ in any available time for you. You are welcome every time.
I will definitely do that. Thank you so much. Okay, thank you for arranging this talk. It was really fun.
Thank you. We make live in Facebook, and the audience with us today rise more than 290 all the lecture time. So it's very, very beautiful lecture.
Awesome.
Thank you.
Thank you.
Thank you.
To be with us. Thank you very much. Good evening.
It's a pleasure.
And bye.
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 Bye. Thank you.
Have a nice day, everyone. Bye-bye.
You too. Bye-bye.
Bye.